So section 13.1 is about increasing and decreasing functions. And this whole idea in chapter 13 is actually a very visual idea. So there's a lot of stuff in your notes that is in math language that I'm going to try to put into English for you instead and draw pictures. So first, let's just talk about what words mean. What does it mean when something's increasing? Two words. What is it doing? Getting bigger, going up. Okay, that's the main thing. Getting bigger, going up. And if it's decreasing, it's getting smaller, it's going down. Okay? We're looking here at well, no, we're not. It helps if you turn the camera on. But we're going to be looking here in a second at three functions. And it's a graph of functions. I didn't give you the equation of functions. There you go. It's three graphs of functions. The first of the three functions is going to be an exponential function. The second function is going to be a linear function. And the third one is going to be a logarithmic function. So if you look at those right there, I'm going to get these as big as I can so that we can see everything clearly. That first function is the exponential function. Okay? And the general form of an exponential function is some number, which I'm going to call a, just because a is a number, raised to the x power. And in this particular case, x is positive. So to give you a way of thinking about this, one of the potential functions that this could be would be 2 raised to the x power. So if you started out with 2 to the 0 power, then that tells you that the y-intercept would be 1, because anything to the 0 power is 1. And then at x equals 1, then a has the value of 2. But at x equals 2, it has the value 4. At the value 3, it is 2 to the 3rd power, so it's 8. When x is 4, it's 2 to the 4th power, so it's 16. When it's 2 to the 5th, it's 2 to the, then it's 32. You can see that it's going up fast, okay? E to the x would behave the same way. It would go up fast. The only difference is e is just a number that's a little bit bigger than 2. It's an irrational number, okay? And the bigger that number a is, the faster it's going to go up. Because anytime you multiply a number by another factor of itself, it gets big really, really, really fast. So that function, as x gets larger, that function is increasing regardless of what the value of a is. Okay, it's increasing. So your x is positive, and it also happens to be in this particular case that a has to be positive. In fact, because if a were negative, well, it would still, depending on whether x was even or odd, it might go negative instead of going positive. So the key idea here is that as your x value approaches positive infinity, as x increases, this function is always increasing, and in fact, this particular function is increasing faster and faster and faster. But regardless of how fast it's increasing, its slope is always positive because it's going up. When things are increasing, their slope is positive. Okay? When things are increasing, the slope is always going to be positive. Now, the middle example is the one that you're the more familiar with, because the middle one is a linear function. And we know that in that function, this number right here, when x is equal to 0, the y value is b. It's got a y-intercept, okay? And we realize, I hope by now, that this function is a straight line because its slope is constant. So rather than the slope increasing as it goes up, in this case, it simply goes up, but it goes up always at the same rate. Okay, its slope doesn't change as you move along your x-axis. So in this case, as your x approaches infinity, that slope itself never changes, but it is still always positive. Okay? And once again, your slope is a positive number. It's just that the slope doesn't change as you move along the x-axis. It remains constant. This third function is a natural log function, or a log. It might not be a natural log, but the third one is a log function. It might be a base 10 log function. It might be a natural log function. All that's different about those is the top one has a base of 10, what's called the common log, and the second one is called the natural log. The graph in A and the graph in C are inverses of each other. Okay, that's the difference between them. They're inverses of each other. That's why they sort of have similar behavior if you think about it. If you were to take the graph of A, if you had it on a piece of paper, and you took that piece of paper and held it up to the light and you turned it not backwards or upside down, but if you kind of like switched it corner to corner, then that's what would happen to it when you looked at it from the back side. It would look more like that. But again, this one is constantly going up, which means it always has a positive slope, just like the others. The value of the slope is positive, therefore that function is increasing. As x approaches 0, the function continues to go up. The different behavior here is that as this one keeps going up, it goes higher and higher and faster and faster. This one starts out really, really fast, where this one kind of starts out slowly going up. This one starts out going up really fast, but then it kind of loses steam and levels out. So this one is actually going to, at some point, it's not going to have a slope of 0, but its slope is going to stop changing very much. It's going to look like it's flattened out. It's going to actually look like it became a straight line. So all of those are increasing. Now I'm going to put those aside for a minute. And we're going to look at the other side of the coin. These functions are all decreasing. And what it means for a function to be decreasing is that it's traveling downhill. As you read from left to right, which is the way we read, then from left to right, or as x approaches infinity, the graph goes downhill. Okay? that means that this graph has a negative slope. It's more negative over here and less negative over here because, once again, on this side, it appears to be flattening out, very much like that graph. Okay, so there's a relationship between those outside graphs. They kind of behave in opposite ways. This is also an exponential function. In this case, x is less than 0. Okay? X is a negative exponent. So what happens is when x is a large negative number, you wind up with a larger value. But when it gets to be more positive, and in this case also, a has to also be, I'm thinking a has to be negative. These are not the important details. I don't want to, I'm only putting up the function so that you'll realize the type of the function. But the key here is to realize that it's always negative. I don't want to give you too many details. So as x increases, this function always goes downhill. And eventually here it flattens out. Just like here, this one flattened out, but it didn't flatten out against the x-axis. Okay? So the slope eventually gets less and less steep, but it still is a negative slope. This is also still a negative slope, but just like the line on the other page that had the positive slope and went uphill, this line is going downhill, but its rate of change it decreases at a constant rate. This is the line like y equals mx plus b, and again, this just simply tells us that that's the point 0b. But it tells us that m, the slope, is less than 0. It's negative. No. And the only reason we won't say that, even though what you are saying is correct, okay, the reason that we don't is because we read on a graph just like we read words in a book. We always read from the left to the right. So that means that when you start, you're not going to start in a quadrant at all. You're actually starting along your x-axis. So it's starting in the second quadrant and moving into, in this particular case here, it actually only moves. It never gets to the first or the fourth quadrant. It only gets to the second and third. And in this one, it only exists in the second quadrant and moves into the first and never gets to the third and fourth. So you have to be careful how you say it. You can't read the one in the middle by saying, well, but if I go the other direction, it increases. Function values are going up, but not as the x values are going up. We're always trying to read it to where the x values are going up, so we'll be consistent in the way that we talk about it. Okay? Is that the question, or did I misunderstand you? Okay. So if we're reading, once again, from left to right, and we're letting x approach infinity, because that's what we're always doing here when we're looking at a graph and looking at the x values. We're looking at what happens as x gets bigger and bigger. Well, what happens as x gets bigger and bigger is this is going downhill, 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 and here it's not going downhill all that fast. But as it gets closer and closer and closer to your y-axis, it's going faster and faster and faster. But it's still negative. It's actually approaching a slope that's undefined because it becomes so steep it's almost vertical. Okay? But the fact is that the slope here is still going to be a negative number. And this, again, that's a log function where the value of the base and the value of the exponent take on certain values. Sometimes it matters whether they're positive or negative, or sometimes it's whether they're between 0 and 1 as to what the function actually does. That's the basic behavior. These two graphs are inverses of each other. If I were to take this one on a sheet of paper and flip it corner to corner and read it from the back, that's the first one is what it would look like. Basically what you're doing is you're folding it along the diagonal. You're rotating it around the line y equals x. Okay? That's kind of a hard thing to visualize. Now what I just told you with pictures is what this says. But this is math language. Essentially what this says is that as long as you have the first number smaller than a second number, like if the first number is 1 and the second number is 5, then if f of 1 is smaller than f of 5, if you plug 1 into the function, you get a number, and you plug 5 into the function, and you get a number. The number you got when you plugged in 1 is going to be smaller than the number that you got when you plugged in 5. That means the function is increasing. Because when x went from 1 to 5, the value of the function went from this place to a higher place. So it went up. It increased. And that's what the definition of increasing is mathematically. This says the same thing, except it says that when you plug in, for example, 1, and you plug in 5, and it turns out that when you plugged in f of 1, you got a number that was way up here. But then when you moved over here and you picked up f of 5, your value, your function, your next point was way down here, so it went down. Your function was going downhill. So that's why it's decreasing. So in order to kind of cement those ideas and talk about those ideas, and as we weave through this, I'm going to bring up things about derivatives, because remember, the slope of a line or a curve is represented by its derivative. Derivatives are slopes. They're a rate of change. They are a slope. So we're going to talk about what derivatives mean to this as we go through. This one says, where is the function increasing? Where is the function going up? Now that means the same thing as where is the slope of the function positive? That's what it's asking us. And I'm going to remind you something about interval notation. On the interval for your x-axis, the x-axis runs up to positive infinity. It also runs down to negative infinity. And every number in between can be used to express an interval. Okay? When we have infinity, we use a parenthesis because infinity isn't actually a number. Infinity just says further down. So it's not really a number and we don't include it. We include numbers in an interval when we have a square bracket. You're not going to see me use a square bracket here because the intervals that we're going to use, we can't contain the endpoints, and I'll explain why as we go along. So the intervals that we're going to use are going to be enclosed in parentheses. They're going to look like points, but all it's doing is we're saying in interval notation we start at a low end, and we go to the high end. Or, in other words, we start at the beginning, and then we say where it ends. Where does the behavior begin? But first, where does it begin? Okay? So, is this function increasing between -4 and 0? How do you know? Because it's going downhill. Okay? So then where is it increasing? Okay, it is increasing from +4 to +6. It is increasing for those x values, and the reason that we know it's increasing is when we go from x equals 4 to x equals 6 on the graph of the function, we moved up. Okay? It went up. So one of the intervals where it's increasing is from +4 to +6. Where's another place that it's increasing? Because it's increasing someplace else. That's exactly right. It is increasing from -infinity because it starts down here, and reading from left to right, it keeps on increasing until we get to 4. So that's the interval, and the reason that that's true is because if I trace along that function, as long as I stay on that interval of the graph, I'm tracing uphill. Now, is it increasing anywhere else? Now, those are the only places I see it going uphill. Okay, remember, we're always going to read left to right. So here's the same graph. Where is this function decreasing? Okay. Because at +6, we're up here, and from there it goes downhill. And from -4, we're going downhill, 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 but we stop at 0. So on this interval and on this interval, all the way up to +infinity, we say that it's decreasing on the interval from -4 to 0 and from 6 to +infinity. Okay? You can put union, or you can simply say and, or you can say or. And doesn't really necessarily make any sense because it can't be this and that. And yet both of those do answer the question. I'm not going to worry about symbols. When I say what is the interval, you can even write out words and say from -4 to 0, from 6 to infinity. Okay? It could be, it's hard to tell.
And it's from 0 to 4, just that tapering out that it's not visibly changing. But
Yeah, when it gets to 0, you really can't, it doesn't look like it really is changing after that. And that's actually going to be the next thing that we talk about. So on the next one, we're going to say, all right, we know what's going on here, right? We know what's going on here. We know what's going on here. We know what's going on here. There's a piece we haven't talked about. So I'm going to use green to mark where it's increasing. That means that's this part. And then I'm going to go back and repeat what we said on the last one, which was that it is decreasing. And I can't tell if it's decreasing with a curve or if it's decreasing in a straight line because I don't have any information about what the actual equation is. But I do know that it's decreasing. From -4 to 0. And when you look here, you can tell why I had to put parentheses and couldn't put a bracket because I can't include the -4 in either one of those. We're going to have to talk about why that's so. But -4 is not included in either one of those two intervals. And then it also increases, excuse me? It does. In fact, this all has something to do with the limits and derivatives. It's also decreasing as we go from 6 to positive infinity. Okay? So here again, we've got that overlap, and we're not including 6 in either one of those. Okay? But our question becomes, what's going on from 0 to 4? It's constant. It is neither increasing nor decreasing. And since we're going to get really tired of writing neither increasing nor decreasing, we're going to say it's constant. Okay? And in fact, when the value of the function is constant, in other words, it doesn't change at all, doesn't go up, doesn't go down, then the slope, this is equivalent to saying that not only is it constant on that interval, but its slope on that interval is actually equal to 0. Okay? The slope of that horizontal part of the function is 0, just as the slope of the negative parts, the decreasing parts, is negative, and the slope of the increasing parts is positive. So we've quantified what's going on that whole entire interval except for 1, 2, 3, 4 places. There are 4 places that we haven't actually said anything about. What is happening with the function at x equals -4? It's not increasing and it's not decreasing. It's changing direction, but for just an instant, if it's not increasing and it's not decreasing, it's also constant. Okay? Just for that one moment in time when it's -4, not -3.999999999, not -4.0000001. It's just for an instant, exactly -4. And at that point, it is constant, and its slope is equal to 0 for just that instant. Not for an interval, but for that one single point. Its slope is 0. Okay? And the same thing happens again when x is equal to 6. Just right on the value 6, just as it gets to 6 and then leaves, for just one instant, it's constant, and its slope is 0. Because the only way you could go from being negative to being positive is if you pass through 0. Because the negative numbers are on the left of 0, and the positive numbers are on the right. So the only way to get from negative to positive is to pass through 0. The only way to get from positive to negative is to pass through 0. But we still have two other numbers to talk about. I'm going to talk about something else before I talk about those other two numbers. This is where we're going to start talking about the derivatives. Derivative and slope is the same thing. From the beginning, we've said that. The derivative is the slope, is the rate of change. The derivative tells you how fast y is changing based on an increase in x. Okay? The derivative is the slope. On this interval, the value of the derivative of that function is positive. On this interval, the value of the derivative of this function is positive. Okay? Since the derivative is the slope, the value here of the derivative on this whole interval, -4 to 0, is going to come out to be negative. Because this slope is 0, that means that the derivative is also negative. Because the slope on the interval from 0 to +4 is equal to 0, all along that interval, the value of the derivative is going to turn out to be 0. Because that is the relationship between slope and a derivative. Now here comes the other 2 points. What is happening to the function at x equals 0 and at x equals 4? At that one single instant, what did the function do? It went from, if we're approaching 0, it went from decreasing to being constant. It changed directions. It changed behavior. Just like it did here, with one very small change. Here, we know the slope is 0, okay? But the difference here is we can't say the slope of a tangent line or the slope of the function is 0, because remember, when I'm talking about derivatives, I'm talking about the slope of a tangent line as well. But look how many tangent lines I can draw. Think back to the test for continuity and the test for when does the derivative exist. Now, the test for continuity is simply that the function can't have a hole. It has to exist in the value. Okay, well, that function exists at that value, so there's no hole. The limit from the right has to come and meet at the limit from the left, which means your limit exists. Okay, well, the limit exists at x equals 0. The value of the limit has to be the same as the value of the function. Okay, well, that's true too. They all come together and there is no hole in the function. So the function is continuous. That's the first requirement for the derivative to exist. You have to have a function that's continuous. That's why the derivative exists here. The derivative exists here. The derivative exists all along that interval, but it doesn't exist at x equals 0. And the reason it doesn't is because at x equals 0, the function didn't make a nice smooth transition like it did the top of those two curves. It made a sharp change. It did, that's exactly right. That was the next point. So you're very perceptive. The same thing is happening at 4. It's going along being constant, and then suddenly it takes off and goes up. I can't draw a unique tangent line at 4 on that function. So at those two places, unlike here where I can say the slope is 0 and the derivative does exist, at those two places, at 0, the derivative of 0 and the derivative of 4 do not exist. There is no derivative at those 2 points. You cannot calculate a derivative because you can't calculate a slope. You can't say what the rate of change is. Okay? Now, all of the numbers that we just talked about are very important numbers. They're called critical numbers. We're going to talk some more in this section about critical numbers. And even though these are not places you can take a derivative, they are still critical numbers. And the reason they're critical numbers is because they're places you can't even take a derivative. And that's why I wanted to point out here to you, while we can see it, the distinction between the slope being 0, which means the derivative does exist, and the slope doesn't even exist because of the behavior of the function. You can't calculate a derivative, because both of those can happen at critical values. That's exactly what it is. The critical values are where the function changes directions, sometimes sharply, sometimes smoothly. Right. At 4 and at 0, that function does not have a derivative. No, it's only if there's a change in the direction of the function. It isn't just a change from 0, it's a change in the direction of the function, where it has to be going from increasing to decreasing, or decreasing to increasing, or when it goes from either decreasing to constant, or constant to increasing, or constant to decreasing. It has to be changing behavior. Yes.
Just trying to think of how at -4 it transitions. We can add 0 and 4, it transitions sharply. What defines the change of it?
And I I can understand what you're saying, because when I look at this part here, there's part of my brain that wants to say that's curved. And if it's curved, it's a smooth change. But if that part of the function, if it was a little clearer on the graph that that function was actually a chunk that was linear, it stopped at the top of that, what looks like the beginning of a parabola, it stopped abruptly and then sharply stopped and decided to be linear, I think there you can make a case that no, the slope is not zero, because it's not making a smooth transition. But because it's so hard to tell since we don't have the function itself, then we just have to assume that it actually curved, but it was just curving a lot more slowly.
So is there a rule or a certain number change in difference to where it would be considered a smooth change to the sharp change, like from 0 to 1 would be considered a sharp, but from 0 to point 1 to point 2 would be considered smooth?
It could be. It would depend on having the function itself. Okay, and we would have to know that from the function. What we're looking at here, without knowing any of the pieces, that's a compilation of a bunch of piecewise functions. And not having the rules for the different pieces of it makes it hard, because we don't know if that second piece of it is linear or if it's maybe a quadratic function or what it is. Okay? Now, when we get to the part about functions, hopefully seeing this visually, though, will help you clarify what we're going to do with the functions and actually finding their critical numbers. The other thing that I wanted to tell you is that I want you to think about finding increasing and decreasing functions, and this language sometimes is a little easier to understand, is if you think of it as, if you've got the graph of your function, if you think of it as a roller coaster. Because on your roller coaster here, you start out the ride here. For the first little bit of the ride, in fact, the first maybe second or so, what's happening? Yeah, you're increasing your height. You're increasing your distance from the x-axis. So the roller coaster is going uphill, okay, which is what it's telling you here. You're increasing. Now, at some point, it's going to get to the top of that hill. This may help kind of get through what we've been talking about, is when is it making a smooth transition. When it gets to the top of the hill, does it just sit there? No, it's still going to be moving. But is there not, at some instant, at the top of that hill, is there not some instant when it is no longer going higher? I think that's the point of the roller coaster. You get to the top of the hill, and what are you going to do? You're going down the other side. That's where the thrill comes in. So even though it's increasing, as you keep on moving, well, that wasn't much of a thrill, but it did decrease. It did get lower. But once it decreased and got lower, at the bottom of that little valley, just for an instant, it stopped decreasing, and then it started climbing the hill again. So for just an instant, the slope was 0, but then it starts climbing again. And as long as it's climbing, the slope is positive. But then what happens when it gets to the top of that last hill? It goes, and it goes down fast. Okay? It not only has a negative slope, but it makes you think you're going to go into a completely vertical slope, an undefined slope, because it's going so fast. Okay? Now, at every one of those transition points, it didn't hit any sharp corners. And if you think about any roller coasters you ever been on, why are there no sharp corners? Why are there no sharp right turns or sharp left turns in a roller coaster? It would jump the track. Because in order for it to have, you know, you're talking about parallel rails that are forming a square. So So you don't want your roller coaster track doing this. Because when you get here, you're going so fast here, you're going to jump the tracks and be off the tracks. Okay? The kind of turns you want it to make, you want it to be nice, smooth turns. I mean, you're still going to think you're going to fall off. That's just the fact. But the reason you think you're going to fall off is because of how fast it's going. Okay? But your roller coasters are always smooth curves. There's never going to be a sharp corner because bad things happen at sharp corners. And in the case of our derivatives, the bad thing that happens is the derivative can't exist. So this explains to you the test, and I'm not really going to go through this too much. I'm just going to try to put it in English. This tells you that when the derivative is positive for a function on any particular interval, that means that the function is increasing. And I've been telling you this the whole time. And that when the derivative is negative on that interval, then the function itself is going to be decreasing. So when the derivative is positive, it goes uphill. When the derivative is negative, it's going downhill. When the derivative is equal to 0, we say that the function is constant. In other words, it's flat. It is a flat horizontal line, even if it's only a flat horizontal line for one single point. So the best thing to do here then is to define the critical numbers I talked to you about and then show you how to find them. The critical numbers for a function, first of all, those numbers have to be in the domain of the original function. The function cannot be undefined at a critical number. So if you've got a place that the function has a hole, a place that's not continuous, a place that it has an asymptote, then there is not going to be a derivative and there is not going to be a critical number for that value. So it's only numbers that are in the domain, and the special feature of critical numbers is that when you take the derivative and set it equal to 0, you can find out what they are. And the reason for that is because the critical numbers are where the function's slope is equal to 0. Okay? And we're going to call those points critical points. So what does that mean that we need to do? Now, I've got a whole set of steps here, but rather than read the steps to you, we're going to come back and read the steps when we're finished actually doing them, because doing them makes more sense than reading and then thinking about what does that mean? How am I supposed to do that? Okay? So, what we're going to do is we're going to find the intervals on which this function is increasing or decreasing. We're also going to look to see where the slope of the tangent line, or when all the tangent lines, or when the function basically has a horizontal derivative, a horizontal tangent line. Okay? That's when the graph is going to be basically constant, and maybe just for an instant. Then we're going to use all of that to graph the function. Now, believe it or not, there were not always graphing calculators. Y'all are all too young to remember. All of you. But when I went to college, there was no graphing calculator. And it sucked. Compared to what I've learned since I had a graphing calculator, I could have learned a lot more if I'd had one. But All we had when I took calculus, even when I did my graduate work, all I had was a little calculator that add, subtract, multiply, and divided. And then I was thrilled when I got in college, and there was a calculator that would actually raise something to a power higher than 2. It was just wonderful. Yeah. Yeah, they did. I never thought it was cheating when they came out with graphing calculators. I was just so happy. I was like, hey, this is wonderful. But I had to learn. I should have brought it down here and showed it to y'all. I still have both of my slide rules from college. I still have both my slide rules upstairs, and I can probably calculate, well, probably not as fast as I used to, but I could probably still calculate almost as fast as somebody with a calculator if I were practicing to remember how to do it, because slide rules, you're just basically lining up numbers and then counting up powers of 10. But anyway, we didn't have graphing calculators, so back when I took calculus, you couldn't figure out what that graph looked like. You had to have calculus to understand how to graph that function, because otherwise it was hard to figure out how to graph it. Because you can imagine if I gave you a table of A's and told you to get me a table of A's for that function going from -10 to 10 that you can graph the function with, you'd be there for a while. And we're sitting there with our little add, subtract, multiply, and divide calculator that won't even raise something to the 3rd power. Okay? So it was tough. We needed calculus to do this back then. Here, I just want you to have the idea. Okay? So with this function that we could graph quickly on the graphing calculator, because this one wouldn't be too hard to actually find a good window, we're going to follow the steps that we need to follow. And I'm going to lay the steps out in front of me so that I can use the same language they're going to use. So our first step for this is we're going to locate the critical numbers. And basically the way that you locate the critical numbers is you take the first derivative, and I use the word first derivative because there actually is a second derivative, but we're not going to talk about what it does or the section that talks about it. That's section 13.3. But you can actually take more than just one derivative. You can take a derivative of a derivative, and then the derivative of that derivative. And you can actually derive some functions completely out of existence. You can take derivatives until they just kind of like blow up and go to 0. We won't have to do that. I had to do that. I had to learn how to do that as a calculus student. So we're going to take the derivative of the function, and we're going to set it equal to 0 and solve it. That's going to be our first step. And that shouldn't be too bad because this is a polynomial function. It's not hard to take the derivative. So you tell me, what is the derivative of this function? Okay. And now that we have the derivative, we are going to set it equal to 0. So that means we need to solve that equation for x. And everybody in here ought to be able to do that because there's 2 different ways to do that. One of them always works, the other one sometimes works, but in this case, the one that sometimes works is probably the easier one. The easier way that sometimes works is to factor that derivative and set each one of its factors equal to 0 using something called the zero product principle. The other way is to use the quadratic formula. Now, you can do it either way. I don't care which way you do it, because I look at this and I see that this is 3 and this is 6 and this is 9. My mind says I can divide all those numbers by 3. So that's the first thing I'm going to do. So there's a pair of factors, and for sure 3 is not equal to 0. So it must be the rest of that stuff that would be equal to 0. So if this is equal to 0, there must be, if it factors, it might have 2 factors, and one or both of those would be 0. So since this is x squared, I know that there's going to be an x here and there's going to be an x here. And since that's a negative 3, I know that the only possible numbers I can put on that other end are 1 and 3. Because that's the only way to multiply 2 numbers and get 3 is to multiply 1 times 3. And since I know that it has to be a negative 3, then it must be the 3 that's positive and the 1 that's negative, so that I get positive 3x minus 1x to be the positive 2x. Now, if you didn't want to factor that and you want to go with the quadratic formula, that's fine. And you'll come out with the same 2 answers I'm going to come out with using the zero product principle, which says that either x minus 1 is equal to 0, so x must have been 1, or x plus 3 is equal to 0, so x would have come out to be negative 3. That's the same answers I would get over here. There wouldn't be any difference. Okay? So I have now found the critical numbers. That's my critical numbers. The critical numbers are where the value of the derivative is equal to 0. Now, secondarily, it's also going to be where the value of the derivative is undefined. Okay? But this function, we didn't have to worry about that because it's always going to be defined because it's a polynomial function. There's no division by 0 and there's no square roots. So what we do with those 2 critical numbers is we put them on a number line. Yeah, the 3 just becomes irrelevant because it's obviously not 0. But if x is 1, then the stuff in the parentheses becomes 0. So 3 times 0 is 0. Or if x is negative 3, same thing happens. The stuff in the parentheses becomes 0, and 3 times 0 is still 0. I just factored out the 3 to make it easier to factor the whole problem. Okay? So what we do is we put our 2 numbers, 1 and negative 3 on a number line. That's our 2 critical values. And then our job is to test points in each piece of the line. Now, I could pick a number down here below negative 3, like negative 3,437,619, but why would I do that? Not that much fun. I don't even want to type that in a calculator. So I'm going to pick negative 4. Okay? I like negative 4. Negative 4 is a nice, small, negative number. I want you to plug negative 4 into 3x squared plus 6x minus 9 and tell me what you get. I heard somebody say 15. Positive 15? Okay. Now, believe it or not, it's not the fact that it's 15 that's important. It's the fact that it's positive. That's what I was interested in. Forgot my prime. What that means then is that the function on the interval from negative infinity to negative 3 is positive. In other words, the function is increasing on that interval. At the value negative 3, the function reaches a valley or a peak, one or the other. Since it was positive, it's going uphill, so we know it's reaching the top, not the bottom, because it's going up before it hits 0. Then the next thing that we need to do is we will test a value that's in between negative 3 and 1. And I don't know about you, but my favorite number to test anytime I have to test is 0. Because 0 makes stuff disappear. So 3 times 0 squared plus 6 times 0 minus 9 is equal to negative 9. And because it's negative, I know my derivative is negative, and that means the value of my function is negative from the time it leaves negative 3 until it pulls into the station at positive 1. So then I need to test a number that's more than 1. And once again, because I'm not crazy about doing any really heavy-duty math, I like 2. And I need to know where is f of 2 as far as positive or negative. And I'm betting it's positive, but I'm not sure that it's positive. The reason I'm betting it's positive is because, well, if it went from positive to positive again, it passed through 0 both those times. So I'm betting it probably this time is positive, because that's kind of what polynomial functions do, is they're roller coasters. Okay? Is it positive? It's 15. Now remember, that's the value of the derivative, not the function. So here I'm positive, 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 positive. Okay? Now the last part that I need to do is I need to graph this function. In order to graph the function, I know a few things. I know that because I used 0 here, I can quickly find its y-intercept. Okay, I know this is the function itself. I know that talking strictly about f of x, I know that if x is equal to 0, that y is equal to 4. That's its y-intercept. That's not hard to find, because 0 makes all the other terms of the function disappear except the constant at the end. The other numbers that I should plug in are the critical numbers, and since I've already used 0 to find my y-intercept, I should also go ahead and use the other 2 test points, because I know what to expect as far as what should happen from one to the next. So I'm also going to plug in -4 and I'm going to plug in positive 2. And at this point, I would want to use my graphing calculator, but I don't, and I think there's one on here. Let's see, yes. I would want to use my calculator to help me do this quickly, because I don't want to grind through too much arithmetic. So my function is x to the third plus 3x squared minus 9x plus 4. And I'm going to set my table up to have it let me ask for x values, because I don't want to see every x value it knows. I want to see just certain ones. So it's set up to let me ask for x values, and I'm going to go look at the table. And I don't like any of those, so we're going to get rid of those. That's from back in Chapter 11. And I'm going to plug in, just to check, in case my brain might have kind of went dead for a second, I'm going to go ahead and plug in 0 anyway. 0, negative 4, negative 3, 1, and 2. So what I have now is I've got a table of values for a few of the points on my function. Excuse me? Did you plug in the function or the derivative? No, I messed up. I messed up. I see where I messed up. I didn't get my x. I clicked it, but it didn't take. Come on. There we go. So at 0, it's 4. At negative 4, it's 24. At negative 3, it's 31. At positive 1, it is negative 1. And at 2, it has a value of 6. So I've got 1, 2, 3, 4, 5, 6 points for the graph, and that's all I need. I don't need, 25 points. I only need those 6. Because once I know those 6, and I know that this is what the function does, and this just illustrates what I was just showing you. This tells me now I can graph this function. See if I can get the calculator out of the way and pull it all together for you. I've got the graph of the function because I have plotted the point 0, 4. I'm sorry, it's 0, 4. I plotted the point 0, 4 from the original function. I have plotted negative 4, 24 on a piece of graph paper. I have plotted negative 3, 31. I have plotted the point 1, negative 1. And I've plotted the number 2, 6, the point that corresponds to 2, 6. And then I know from my derivative test that on the interval from negative infinity up to 3, my function was increasing. It was going uphill. So I'm actually going to start at 3 just because it's easier to draw. I'm going to draw backwards, but I make my function increasing. Okay? So it's increasing there. I also know that it's increasing on the interval from 1 all the way up to positive infinity, and that it's going to go through the point 2, 6. So I make it increase on that interval as well. Okay? I also know that on the interval from -3 to +1, which is from here to there, I know that function decreased. And that it starts up here at the top at 331, and it decreases and decreases and decreases and decreases, goes through the point 0.04, because that's the y-intercept, continues to decrease until it gets to the point 1, -1. Now, you know why people that went to college when I did have such wonderful graphing skills. Because it took us a half an hour to draw a graph. Just one graph. Okay? Now, one of the things that you should always do once you've actually drawn your graph, sketched your graph, is it never hurts. Since this is the function, you might want to make sure that your graph actually looks like that. So given what we know about the numbers that we've got here now, we realize that there's not a lot to see below the x-axis. So when we go to the window, we might only want to go, since our critical numbers didn't go all that far, we might only want to go to like maybe -6 and up to about +6, because we know that's where all the action's happening. We don't need to have a very big domain to see everything the graph knows how to do. And we don't really need to go all that far negative, maybe only to about, I don't know, -5. But we do need to go pretty high up, because we know the point -331 is on that graph. So we probably want to go up maybe as far as 40 or 50. So let's see if the graph on our calculator looks like the graph that we drew. Did we do a good job? But look how much faster that was. The calculator is actually only faster because it can do the arithmetic so much faster. That's really all your calculator is capable of doing. It's not capable of doing anything else but arithmetic. It's able to translate its arithmetic into graphs and other things, but it's only because it's really good at arithmetic. So there is your complete set of steps for how you actually construct a graph using the critical numbers and your derivatives. Now, that was nothing to be really all that impressed with, because, as you can see right there, that graphing calculator did a wonderful job of drawing it, and we didn't have to do, I mean, even if I had just hit the standard window, I get a pretty good idea of where that graph is and realize all I need to do to see everything that graph knows how to do is to raise the window up. So you're sitting there saying, so why did I have to learn how to do this with calculus? Well, because that one's not that easy. Unless you've drawn a lot of graphs in your time, knowing what the cube root of x minus 1 squared looks like is a little bit ticklish. Oh, do you not? I have a copy of your... Well, we'll just change that one. Well, okay, you change your example, you change yours, because this one's actually easier to do, and it'll show you the same thing, so change your example. So we're going to follow the same process we followed a minute ago. We're going to find the first derivative. Can everybody find the first derivative? This is just it's a chain rule function, but it's not a hard chain rule function. The reason it's not a hard chain rule function is the derivative of your inside function is just 1, so it kind of conveniently excuses itself and gets out of the way. Okay? So it's 2/3 times x minus 1 to the negative 1/3. Now, you can simplify that function, but it doesn't make it a bit easier to figure out what it's going to take for that to be 0. Because 2/3 is never going to be 0. And the only number that, regardless of what power you raise it to, whether that power is a fraction, a positive number, a negative number, whatever, the only number that is ever going to give you 0 from those parentheses is going to be 0 itself. Because the square root of 0 is 0, the cube root of 0 is 0. There's just one little bitty problem that you're going to have to think about. You have to be careful about. So it looks to me like that this is only going to happen if x minus 1 is equal to 0, which would imply that the critical number is positive 1. Okay? Now, the only thing you have to be careful of, and this is just a caution, it doesn't actually change much, this is just a caution, is about that power being negative. Because that power is negative, this derivative is actually over 3 times x minus 1 raised to the 1/3 power. And in the case where x is actually 1, your derivative is actually undefined when x is equal to 1. Okay? It's actually undefined. Now, we set the derivative equal to 0 and found the critical value, but it turned out that the very number that it took to make the derivative be 0 was actually not in the domain of the derivative. It made the derivative undefined. I want you to remember that. Okay? We didn't do anything wrong. We're still going to use that critical value. Just remember that it made the derivative undefined. It did not make the function undefined. Or not 0. I'm sorry. Wrote that wrong. F of 1 is equal to 1 minus 1 to the 2/3 power, which is also 0. So the function is defined at 0. That's not a problem. The function is defined, but the derivative is not. That's what I want you to remember. The derivative was not defined, because it's going to make something a little odd happen. So just remember that we found this. Because the graph that you get is not going to look at all like what you're going to think it's going to look like. Everybody's always surprised when they get the graph, and I remember now why I changed this example. I think the other example you got does it too. You can try it out. But I think your example does the same thing this does. This one is just easier to work with. So we've got one critical value. Okay? That means that we take our critical value, just like we did before. We put that critical value on the number line. And then we plug numbers on either side of 1 back into the derivative to see what happens. And because we don't like using any more weird numbers than we have to, one of the numbers we're going to plug in is going to be 0, and the other one's going to be 2. Okay, we're not going to get real creative. So f prime of 0 is going to be 2/3 times -1 to the -1/3 power. And since we already know we can use the calculator to find these things, let's just do it this way. Now, we could actually use n deriv here since we're going to do this numerically, but I'll plug in the derivative. So there's the derivative the way that we figured it out. If you want to make sure that you did it right, you can always go math down to number 8. Tell it the original function is, scoot this back over here. The original function is x minus 1 raised to the 2/3 power. Yeah, it's not the right symbol. Must have hit second before I hit it. So there's x minus 1 raised to the 2/3 power with respect to x for all values of x that I ask it for. And then we'll go to the table. And hopefully the answers we get in y1 and y2 are all going to be the same. You see that for the numbers we plugged in before, they are. And since one of the numbers we're looking for is 0, it's -2/3. -0.6667 is -2/3. And it's not that it's -2/3, it's the fact that it's negative. We're interested mostly in the fact that it's negative. Okay? That means on this side, on this interval from -infinity to +1, f of x is decreasing. Its derivative is negative. Okay? And since the number 2 is already on there, and notice here, on y2 it said that the value of the derivative is 0, but on y1 it says there's an error. That's because of the difference in the ways that I put it in. At the value 2, the answer is positive. Okay? So f of 2 is positive. So looking at that, what I'm tending to expect is if I don't know anything about the way that function is going to look, I'm thinking, well, here's what's going to happen since it's going to be negative on one side of -1, and I didn't make it go up far enough, and positive on the other side. That means it's going to be coming downhill on this side and then going back uphill. That kind of makes sense to me, right? Does that make sense to everybody? That's kind of what it says it's going to do. And you look at that and you think, that looks like a parabola. Well, that's not what the graph looks like. That's why you use some other points.
why is all this other stuff up there? Go away. There's what your graph looks like.
Is it doing what the derivative test said it was going to do? Yep. Decreasing to the left of -1, it's increasing to the right of -1. What step did I skip? When I did this, I should have gone back here, and besides finding f prime 0, I should have also found f of 0. At least for 0 and 2. And in fact, it might have been better if I had found it for maybe a couple more numbers, just to be sure. Like maybe -1 and 3. So I'm going to turn the derivative off because I don't care about its values anymore. And what I'm going to do here is I'm going to take out the end derivative stuff and just keep that function. So I can get some values to plot on my graph. So when I go to my table, I see that my table of values says that when x is 0, the value of the function is 1. And that when x is, we'll just add that one on in, I didn't have it on there, but when x is -4, it's like 2.9 something. And when x is -3, it's 2.5 something. And when x was 1, it was 0. Well, we already knew that. And when it was 2, it was 1. What was it when it was 3? Let's see. About 1.6. And then I didn't do -1. And it was about 1.6. So now if I had plotted these points, this might have made more sense. Because here I've got the point 0, 1. When it's 2, I've got 1. But when it's -3, I have 2.5. And when it's -1, I've got 1.6. And when it's +3, I've got 1.6. And when it was -4, I've got 2.9. And, you know, I could have also added the fact that when I was at +4, I would probably also have gotten another number that was around 2. So we could have added a few more points if we wanted. But clearly the points that I'm showing you here wouldn't have tempted you to try to connect that up with a smooth curve, would they? The only thing they would have tempted you to connect it up with was straight lines. What do we call what's happening when x is equal to 1? Is the function continuous? Yes. Is it a smooth curve? No, it came to a sharp point. Okay? that means the derivative is undefined at that point. Okay? Which we noticed as we went through with our critical number and found our critical number. The function was defined as the critical number, but the derivative itself wasn't. Okay? And this also brings up something else I want you to pay attention to. This is a warning to you. What does the calculator say the value of the derivative is at x equals 1? 0. What does our version of the derivative say that the value of the derivative is at x equals 1? Undefined. Okay? The problem with the calculator doing in derivative is it is a wonderful thing. It's a great tool. It saves you from lots and lots of work most of the time. But be wary of it, especially if you get an answer that doesn't seem to make sense in the context of the problem you're looking at. Now, this one we'd have had no way of knowing that didn't make any sense if we hadn't actually paid attention and taken the derivative ourselves and plugged it in and tried that. But a lot of times the calculator will give you a numerical answer for a derivative when in fact that is not the value of the derivative, and in fact the derivative may not even exist. Okay? So be very cautious of that. And in relation to the test, there's one other thing that you may have noticed. I don't remember, I don't think y'all had this one, but there is one version of this test that where I ask people to find the equation of the line, the tangent line. Two of the examples of that gave you derivatives, and one of the derivatives was in scientific notation, and everybody was like, they were trying to use the first two digits of it and saying, okay, this is the slope. Well, in scientific notation, that wasn't the slope. The slope was actually like 1.56 times 10 to the negative 25th power. And they're trying to use the slope of 1.56, and they're getting a really strange looking line, and it's not working. And they're all freaking out about it. So I had to say, you need to look at the whole number. You can't just look at the first two digits. You have to look at the whole number. And then they realize, oh, the slope of the line is 0. Okay? So be careful of things like that, because sometimes numerical derivatives can give you what looks to be like a really insane value, and sometimes it can even lie to you. It'll give you the wrong value, because NDeriv isn't doing calculus. What NDeriv is doing is it does what the definition of a limit says to do. NDeriv takes the number you tell it to take a derivative at, and it goes a little bit on this side of it, a little bit on this side of it. And it does arithmetic, finds out the value. So then it goes again, and it moves in a little closer. It does arithmetic on this side, and says, okay, there's still a difference. Arithmetic on this side, no, the answers aren't still the same. Arithmetic here, until it finally gets so close to the value you have that it doesn't see a discernible difference in the answer. So what it thought there was when it got closer and closer to 1, the value got so close to 0, it said, it's 0. But it's not. It is not. Okay? So just a word of caution. Sometimes your calculator will lie to you. Okay, we may not get through 3.2 tonight, but 3.1 is the most important one. 3.2 is a piece of cake if you got 3.1. When does this function increase and decrease? And we're going to follow the same process one more time. Now, before we actually follow the process, I want you to tell me, what do you think this function is going to look like? be a parabola? Is it going to be roller coaster function? What's it going to do? How's it going to act? What are you worried about happening? Oh, you ought to be worried about something. That's right. You got to worry about the two commandments of math. Thou shalt not divide by zero, number one. Is there potential we would divide by zero? Yes. If x is equal to -1, we're going to divide by zero, which then tells you that the graph has an asymptote at that value. It has an asymptote at -1. Remember that. Find the intervals for which this function increases and decreases. Now, this is a quotient rule problem, but fortunately, like the other one that we had, finding the derivative of this particular quotient rule isn't as hard as it looks like it might be. It's the denominator times the derivative of the numerator, which is conveniently 1, minus the numerator times the derivative of the denominator, which is conveniently 1, over the denominator squared. Okay? Start with the denominator. Actually, the way I taught you to do it was start with the denominator of the derivative and square the denominator of what you had originally. Then take that same thing and put it in the numerator and multiply it by the derivative of the numerator. And then subtract the original numerator times the derivative of the denominator. Okay? There's actually a little rhyme that my calculus students used to make, that they made up for this. And you have to think about why it makes sense. This is high, and this is low. Okay? So this is low d high, low times the derivative of high, low d high minus high d low over low squared. Now, because of all these 1's up here, we actually can simplify this a whole lot. This is x plus 1 minus x minus -1 is plus 1 over x plus 1 squared. And x cancels x, so 1 plus 1 is 2 over x plus 1 squared. There's your derivative. So here's the hitch. F of -1 does not exist. In addition, f prime of -1 does not exist. Okay? This time, neither one of them exists. Last time, the derivative didn't exist, but the function did. This time, the function doesn't exist either. But it's still a critical number. So we're still going to do the same thing we normally would do. We need to set 2 over x plus 1 squared equal to 0 to find our critical value. Okay? So when would 2 over x plus 1 squared ever be equal to 0? Now think carefully. That's a fraction. 0 over 1 is still 0, right? If you cross multiply, 2 times 1 is 2,
But 0 times x plus 1 squared is 0. Is 2 ever going to be equal to 0? Nope. What do you know about what happens when you get a math statement that doesn't make any sense trying to solve an equation? Calculator says error. Your brain says this doesn't make any sense. 2 does not equal 0. Okay? There is no solution. There are no critical values for f prime of x is equal to 1. We can't find one. So at this point, the good calculus students, we're all digging back through our notes saying, okay, wait a minute, what did it say about critical numbers? Didn't it say there was always critical numbers? What did it say about critical numbers? And I fixed up all my papers, so I'm not finding the slide I'm looking for. Here we are. The critical numbers for a function are those numbers in the domain of f, and we have -1 is not in the domain of f, for which f prime of c is equal to 0, or f prime of c does not exist. Does f prime exist for all other numbers? What does this mean about f prime existing at the value -1? Does it exist? No. F prime of that number did not exist. That's one of the reasons that one of the things you do is you start finding your critical numbers is not just find the derivative, but also look in your function to make sure if there's any discontinuities in your function that you know where they are, because that may be a critical number. So our critical number actually is -1, and it's the only one we've got. That's where the asymptote is. That's our critical value, and we're going to look and see what the function's doing on either side of it. So our first function, and I'm not going to use nderiv this time because we already found the derivative. Our first function, our original function, is x minus 1 divided by x plus 1. And we're going to make a table of values, and the nicest number on this side of it would have been 0, because it's easy to plug in 0, and even the calculator can do it faster than I can. I'm sorry, not on that side. That would be -2. And on this side, it would be 0. Okay? So we're going to go to the table, and the only values we're interested in, since we got, and you notice that we got an error when we plugged in -1. So if we plug in -2, we get 3. That means on this side, the function's increasing. increasing from negative infinity to negative 1. And if I plug in 0, it says it's decreasing. So it actually shouldn't surprise us then when our graph looks like this. Because we talked in the beginning, we said we know that it's we know it's one of those rational functions, so it's one of those that does that weird behavior around negative 1, the asymptote. So we could have plotted a few more points, and we would have plotted a few more points. But we see that on this side, the function on the interval from negative infinity to negative 1, it is in fact increasing because it's trying to approach negative 1. And then on the interval from negative 1 to positive infinity, we would see that it is in fact increasing. It's doing exactly what we thought it would do. And the only thing that we would need to do to get that graph is to pick a few more points around fairly close to the critical value. So using points close to the critical value, so we've already used negative 1, so we'll skip over negative 1 and go to 0. And 1. And 2, and see that that's what's happening. Okay? So it will give us some points to plot to verify that the graph looks like what we see that it does. And it's always easiest to use your calculator to get your table of values. I don't expect you to sit there and chug through all that arithmetic. Just remember what you're plugging in is back into the original function, and that you're using numbers that are fairly close to where your critical value is, because that's the only part you're interested in. Now, the reverse for the test of increasing and decreasing is not true. This is just another caution. It's possible for a function to be increasing on an interval even though the derivative is not positive at every point on that interval. For example, if you look at this function, this is f of x equals x cubed. This function is constantly increasing even though at this point the value of the function and its derivative is equal to 0. So what would happen in a graph like this is that you would find that the critical value was at x equals 0. So then you would test a negative number for the derivative, and you test a positive number for the derivative, and find out that both of them give you positive results. So once you found that out, still the same thing to do as what I just told you to do. Put that function back in your calculator and check some values around close to that critical value to get some actual points and confirm that it is increasing and decreasing like you think that it's going to. Okay? And notice that the reason that that function is constantly increasing is because the derivative is 3 times x squared. And it doesn't make any difference what you plug in for x as long as x is not equal to 0. The derivative is always going to be positive because when you square x, it's always going to be positive. Okay? And this just tells you about finding the value of the function at points, and I've already told you to be cautious of that. So the last thing we're going to do, and then I'm going to let y'all go home, and we'll continue on with this next week, and we may have to actually, it would be probably good to have the time and not do the test till the first week of April. So we'll have plenty of time to cover this. So in this example, since I've made you sit there all this time, we'll finish up and go home. Companies selling computers finds the cost per computer. Okay, the cost per computer. That is another way of stating the average cost. Okay? Cost per computer. It's also a way of saying the rate of change, so you have to be very cautious about which one you're going to need to use it for. It decreases linearly. Okay, here's a picture of decreases linearly. When you see the words decreases linearly, your brain should immediately envision a line with negative slope. If it's linear, it's a line. If it's decreasing, the slope is negative. It decreases with the number sold monthly. So it's decreasing as X increases. And it decreases from $1,000 when you don't sell any to $800 when you sold 1,000. And you know at some point, not too far past that, you're going to be hitting zero, which means that your cost is going to become negative, and that makes no sense. Keep that in mind. That means your cost function is no longer valid. So keep the common sense going. The average cost function has a y-intercept of 0, 1,000, and a slope of negative 200 over 1,000, which is equal to negative 0.2. And the reason that they know that, just to make sure that everybody's on the same page, it dropped from 1,000 to 800, so 800 minus 1,000 is negative 200, and this is going from none sold to 1,000 sold. So 1,000 minus 0 for the denominator of your slope is going to still be 1,000, and negative 200 over 1,000 is negative 0.2. Now, the question is, what is the average cost function? Now, that shouldn't be hard to figure out because they've told you everything you need to know. What is the average cost function? They told you it was linear. What's the slope of the average, not the cost function? What is the slope of the average cost function? What's the y-intercept? $1,000. That's why I drew you the picture. Okay? When your variable is 0, none are sold. Okay? That's your average cost function. Then it says, so what is the cost function? Because the average cost function is, this is in dollars. dollars per computer for X computers made. Okay? The average cost function is? Okay. Let me go back and look at the notes for a second. I never did log into Shobi. I wonder if that's a typo. Ah, I remember why now. No, it's not a typo. I said that cost per computer can bring to mind average, because that is, when you have average, that is a cost per computer. Okay, but it can also be the slope of the cost function. Okay? That's the marginal cost. So the average cost function would have the x squared, because the cost function would not. The cost function should be x times the average cost function. That would be x squared. And because your cost function is c of x times x, that's your actual cost function, your average cost times x, that gives you c of x, then that's where the x squared comes from. This x squared is a typo. The average cost is just negative 0.2x. That x squared up there doesn't belong there. Okay? Because this is your average cost function, and it says your average cost function, the cost decreases linearly. Okay, so that makes sense that it's not going to be squared.
So the average cost function is the cost function factor.
Yes, that's the one that should have the x squared in it, not the one up above. So you take your average cost per computer, there's your cost per computer, and when you want to find your cost function is actually the cost for X computers. And the way that you find the total cost function is you take the cost per computer, which is your average cost function. That's the cost per computer. And then you multiply it by how many computers you sell. Okay? So that's a typo, and I'm pretty sure that one actually came out of the textbook. I'll have to go back and look, but I think that's actually that way in the textbook. And I kept forgetting to go in there and do some digital whiteout on that. So your actual cost function then is the negative 0.2x plus 1,000, which is your average cost function, times X computers. Okay? Now notice that it specifies too that is only that's only valid from 0 to 1,000. The reason that would only be valid for 0 to 1,000 is because if you make 1,000 computers, then your profit is going to be 0. Okay? And I'm sorry, I said profit. Your cost is going to be 0. So after that, you can't have negative costs. So past 1,000 computers, the cost function doesn't work. Okay? So then what we do is we suppose that revenue can be approximated by this number, by this function. Now, revenue is the money you bring in from selling those computers. Remember, this is what the computers cost you. This is your revenue in dollars. And both of these are on the limited domain that X can only go from making and selling none to making and selling 1,000. Find the intervals where the profit is increasing. That's your revenue minus your cost. So your revenue function minus your cost function, which is going to be the opposite signs here. So that's going to be positive 0.02x squared and negative 1,000x dollars because you're subtracting those. So your profit function, P of x, that's your dollars total profit for selling X computers. Would you care when your profit is increasing? You care. You care as long as it's increasing. You want your profit to go up. You also will care when your profit starts decreasing, right? In fact, what would you like most to know about your profit? How much it's increasing by, and when is it going to be the highest? When is the value of the derivative going to be 0? Okay? Because that's what you want to hit. You want to hit that many computers. Okay? So find the intervals where the profit is increasing. Well, that means we need to find the critical values for this function. So that means we need to take P prime of x and 3 times 0.0008 is 0.0024. Now, y'all with calculators, check me on this, okay? So your derivative is positive 0.0024x squared minus 4.4x plus $1,400 per computer. And that would be 0 there's only going to be two potential values for x. Now, I don't know about you, but I don't really think I want to factor that. That does not look like something I will be the least bit interested in. So if I was going to do that, I think I would want to do quadratic formula. If I was thinking ahead, I actually gave you the answer on the notes, but I bet I didn't. Nope. Dagnabbit. Okay, here we come, calculator. This is A. That's B. That's C. And there's B squared minus 4AC. This is going to give us the value of x. So the opposite of B was positive 4.4, plus or minus the square root of whatever this is. That's 5.92. Over 2 times A, and 2 times 0.0024 is 0048. So 409.8. Now realistically that should be a whole number, okay? Even though in the function it's a decimal number, realistically when x represents how many computers, you don't make 409.8 computers. So realistically the critical value is 410, okay? And then the other one would be $14,024. So those are your two critical values. And this is where we say thank God for calculators, because we don't want to have to do any of this arithmetic in our head if we don't have to. So we've got our two critical values, and before I do anything, I'm going to go ahead and type those in my X list. So my first critical value is 410, and the interval is going to go from 0 to 410 to 1424 is not in the domain. Because remember it says down here, x can only go to 1,000. So we really can't use the top critical value because it's greater than 1,000. It's not in the domain of the function at all. Okay? That actually is where our cost becomes negative, and that's not realistic. So we're only going to use the 410, and that means we need numbers on either side of 410, and staying within the limits of 1,000. So our first critical value our only critical value is 410. We can pick anything less than 410 all the way down to 0. Well, 0 is easy. And then the top value is 1,000. So that makes the choice of your test points easy. Now, we could do the calculator part 2 or 3 different ways, but since we've already calculated the derivative and calculated the profit function, I'm not going to make you do it with inderiv and all that stuff because we've already seen that there can be problems with doing inderiv. So we're just going to type those in. So our profit function is 0.0008x raised to the third power subtract 2.2x squared plus 1,400x, and then our derivative of that function is 0.0024x squared minus 4.4x plus 1,400. So I plugged those in. This is Y1. That one's Y2. That way we'll go ahead and we'll build our table that has our critical value test, and it gets us the points for our function if we need to. So we're going to go ahead and go over here to the graph. So if you're plugging it into Y1, then Y2, just put X twice. Just put X twice. Because it's saying for all values of X. Okay? So this tells me that on my number line interval, this is what's happening. Here's 0. Here's 1,000. That's my whole entire domain. I can't go outside of that. $410 is down here. It shouldn't be a big shock that at $410 that the value of the derivative is negative 0.56, because remember, I rounded that off. Remember? I rounded that off. If I go up here and I try to put in some more of those decimals, it might actually get it closer to 0. Let's see, it was the negative one. Okay, no, I still have it there. 409.7. Let me write it down here. $697,891. So I'll plug that into the table instead of the 410. After it gets done trying to graph all that. Okay, and so you can see there it actually, if I keep all the decimals, it really is really close to 0. Okay? But realistically, you can't make that many computers. So it's either going to be 409 or 410. And in fact, you'll notice that there's going to be a sign change for 409 and 410. Your profit's still increasing at 409. It starts to decrease when you make the 410th computer. So make 409 and stop. Okay? because your profit is increasing from 0 to 409.7 yada, 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 and it decreases after that, it becomes negative. So the best place to stop is when your profit is $259,317, which happens when you make 409 computers. And actually at 409 computers, it's $259,316. So you lost a whole dollar by not making that part of the computer. Okay? Now that's the point of the problem. That's why this is important. You need to be able to find when things are at their maximum and when they're increasing, like when you have profits, you want it to increase. But you don't want it to decrease, so you need to know when you should stop. And then the same thing with cost. You would like for your cost to be low. But you know your cost can't ever be negative, and there's going to be a point at which your cost is going to increase because you're making too many, and your cost is going to start rising again. So you need to know when you've hit your minimum cost. But mostly you're mainly interested in this kind of problem because the bottom line is not cost or revenue alone, it's profit. What is happening to your profit? Okay? So that's actually pretty much that whole problem. And if I had looked ahead, I would have went ahead and showed you that you can actually graph that on that window. So that'll be in the, I don't know if it's in the notes or not, but that will, I'm leaving it up there while so it can be in the recording. So when no computers are sold monthly, your profit is logical. If you don't sell any, it's zero, right? Makes sense. And when 1,000 is sold monthly, your profit is negative. Or actually very little. It's about to become negative. It's very, very small. Yeah, it's like negative 600. So you should have quit before you got there. Okay? Y'all are very patient. You get your 15 minutes at the end of the night, but maybe that'll get you home in time to get a little more rest.